A star could swallow our entire solar system out to Jupiter. That's the scale we're talking about, the true scale. You're going to meet 30 stars. Each one is thousands of times larger than our sun. And you'll learn about the forces, the incredible forces that govern their lives, their brief, spectacular lives. How do they grow that large to such impossible sizes? And what cataclysmic fate is waiting for them, for every single one? By the end of this, your understanding of the universe, it's going to be reshaped. Permanently reshaped. What does true cosmic power look like? That reddish glow in Orion's shoulder, that's Betelgeuse, a red supergiant. It makes our sun look like a tiny speck. Its diameter is about 1,000 times larger than the sun. 1,000 times. To get a sense of that scale, imagine placing Betelgeuse where our sun is. The star's surface wouldn't stop at Earth. It wouldn't stop at Mars. It would reach all the way out to the asteroid belt. It would swallow the first 4 planets. Just like that, and this isn't some distant idea. It's right there in the sky, but Betelgeuse is more than just big. It's unstable. Its brightness changes. It rises and falls in this slow, irregular pulse. That pulsation is a sign. It means the star is in its final chapter. Stars live by fusing elements in their core. Betelgeuse has almost used up its primary fuel. Now it's this swollen thing, fusing heavier elements. It's a short-lived struggle against its own gravity. And that struggle is ending. Astronomers agree Betelgeuse is headed for a supernova. It could happen tomorrow. It could happen in 100,000 years. When it does, the star will release a catastrophic burst of energy. For a little while, it could shine as bright as a full moon, visible even during the day. A temporary new sun in the sky that makes Betelgeuse more than just a landmark. It's our closest laboratory for watching a supergiant die. Every flicker in its light, every change in its shape that we see through telescopes teaches us about the final moments. Before a star tears itself apart, it shows us the constellations aren't a static backdrop. They're a living theater where titans are born and live and die. So we leave this unstable giant in our backyard and we look deeper into the galaxy, because if Betelgeuse, a star that could swallow our solar system, is just the first entry, then what scale are we about to find next? Betelgeuse is large, but it's not the largest. For that, you look to Canis Major. There's a star there, WOH Canis Majoris. It's on a different scale. If you went around the sun at light speed, that trip takes about 14 seconds. For this star, that same trip would take over 8 hours. 8 hours, that's not just bigger, it's a different category. Astronomers call it a hypergiant. Its radius is somewhere between 1,300 and 1,700 times the sun's. If you put it at the center of our solar system, its surface would go past Jupiter. It would approach Saturn. That volume is so immense it challenges the physics of a star. Something that large shouldn't hold together, and in many ways it doesn't. WOH Canis Majoris is a pulsating variable star. It swells and contracts. With each pulse, it loses staggering amounts of material. It's not a calm sphere, it's a furious, shedding titan. It casts off huge clouds. They form a vast nebula around it, a glowing shroud. This extreme mass loss is the key to its fate. Stars like this are so large, so luminous, that the pressure of their own light pushing outward overcomes the gravity holding them together. They push themselves apart. Studying this hypergiant is like watching a star in its final, unstable phase. It teaches us about the theoretical upper limits of stellar size. There's a line where a star becomes too big to sustain itself. WOH Canis Majoris is dancing on that edge. It shows the largest stars aren't serene. They're turbulent, self-destructive forces, destined for a spectacular end. And if our own galaxy's scale feels overwhelming, Consider that some of the most colossal stars we know aren't even in the Milky Way. Our galaxy's hypergiants, they're not the end of it. To really see the scale, you have to look outside the Milky Way. Out in the dark, about 160,000 light-years away, there's a satellite galaxy. The Large Magellanic Cloud, and inside that, in its clouds, there's a star that changes what colossal means. It's called WOH G64. You don't really see this star. It's shrouded, wrapped in this thick, dense ring of dust and gas that it threw off itself, like a titan in its own cosmic cocoon. That shroud makes it incredibly hard to measure. The light from the star struggles to get out, but the estimates from careful work, they're staggering. WOH G64 is a red supergiant. Its radius is likely over 1,500 times the Sun's. If you put it in our solar system, its surface would go well past Saturn's orbit. It's one of the largest stars by volume we've ever found, and that cloud around it isn't just an obstacle. It's a legacy. The star is so massive its outer layers are unstable. It's shedding material at a phenomenal rate. That expelled gas and dust forms this vast nebula, a thick ring around the star. Inside that cloud, under the Titan's radiation and gravity, molecules are clumping, dust grains are colliding. This chaotic shroud, which came from the star's demise, it's quietly becoming a nursery. A place where the seeds of future solar systems are starting to form. New stars, new planets. This is the grand cycle. A giant nears the end. In its final act, it enriches the galaxy with heavy elements. And it provides the raw materials for new beginnings. WOH G64 shows that the largest stars aren't isolated monsters. They're architects. They reshape their entire corner of a galaxy. They forge the elements for future worlds. They build the foundations for life that might come billions of years later. This dusty behemoth in another galaxy teaches that. The universe works on a scale of both destruction and creation, linked together. But for all its immense size, WOH G64 isn't the most luminous star we know. That title belongs to a different kind of giant. One so bright it sparks debate about what it even is. Luminosity shows a different kind of power. There's a star in Cepheus, RW Cephei. It burns with the light of several 100,000 suns. That's the main thing about it. That immense brightness, almost impossible to grasp. Its size is debated. Estimates go from 1,000 solar radii up to 1,500, but its brilliance isn't in question. It's a hypergiant, a star so luminous it pushes the limits of what a star can even be. And that incredible output comes from a frantic, unstable engine. RW Cephei is semi-regular variable. Its brightness doesn't just flicker, it rises and falls in great, slow waves. Over hundreds of days, that variability is a clue. It tells astronomers the star's outer layers are churning, not a calm surface but a turbulent sea. A bubbling sea of plasma, and this immense, fluctuating atmosphere is what makes the star so hard to measure. From our distance, it doesn't look like a sharp point. It's a fuzzy, shimmering ball of light, so pinpointing where its surface actually begins versus where its hazy atmosphere ends becomes a monumental challenge. RW Cephei shows a fundamental truth about these giants. The largest stars aren't neat textbook examples. They're messy, complex, shrouded in their own brilliance. They force science to confront uncertainty. Every observation, every new measurement is an argument with the data. This star teaches that discovery at the edge of physics isn't about finding simple answers. It's about refining the questions, learning to measure what seems unmeasurable. And while RW Cephei's light dominates its corner of space, its name is just a catalog number. The next star carries a name from ancient mythology, a name that speaks to its commanding presence in the night sky. Antares glows red in the sky, a deep, fiery red. It's the heart of the Scorpion in Scorpius, a red supergiant. It's about 550 light-years away, and its size is immense. Its diameter is something like 700 or 800 times wider than our Sun. If you put it where our Sun is, its outer layers would reach out past Mars, maybe to Jupiter. That red color means its surface is cool for a star, but Antares has a secret. It's not alone. There's another star orbiting it, a companion. This companion is small and hot and fast, a blue-white star. They're a binary system. A dance of opposites, the small, hot star whipping around the big, cool one. That makes it a kind of laboratory. Astronomers can watch how these two different stars interact, how their stellar winds collide. Antares itself is unstable. It's in a late stage. It's shedding its outer layers, building a nebula around itself, and that's a slow countdown. This star will end as a supernova. One day, maybe in 1,000,000 years, that red heart will disappear. There'll be a flash, a piercing light, visible even in daytime. A final testament. For now, it's a link. The ancients called it Antares, a rival to Mars. Today, it's a touchstone. It shows us the dramatic life of a nearby giant. From this brilliant, dying heart, we look to another star, one that's not just in a nebula, but is actively sculpting its own. In the constellation Monocerotis, there's a star called V838 Monocerotis. In 2002, it had an outburst, not a supernova, not a regular nova. It was a different kind of flash, a brilliant, mysterious one. And after that flash, the star expanded. It swelled up, its outer layers moved outward incredibly fast. Within weeks, its radius grew to maybe 1,500 times the Sun's. For a moment, it was one of the largest stars we've ever seen. But then, after the flash, something else happened. The light from that event began moving outward, and it started to hit shells of dust the star had shed earlier in its quieter life. These shells, one after another, they lit up. From our perspective, it created this expanding halo, a light echo. That's what it's called. It wasn't new material exploding. It was illumination traveling through old debris, showing the stars past. For years, telescopes watched this shell get bigger and fainter. The thinking is that event was a stellar merger. Maybe the star consumed a close companion or a giant planet. Or it could have been a final, violent pulse from a dying star. V838 Monocerotis tells us stellar size can be explosive. It can be transient. It can change on a timescale we can watch. A star can become a titan in months, not millions of years. It shows the cosmos is dynamic, always changing, and that kind of explosive growth leads to another question, about a different kind of bigness. What about stars that aren't just vast in volume, but are incredibly dense? Incredibly heavy, where size is matched by mass, where size is even defined by it. Mass is a different scale. There's the Tarantula Nebula in the Large Magellanic Cloud, a place where stars are forming, and in there you have R136A1. By volume, it's not the biggest. Its radius is maybe 30–40 times the Sun's, but its weight is something else. It has over 250 times the mass of the Sun, all packed into that sphere. It's the most massive star we know of, and that mass means power. It shines with the light of almost 9 million suns, one star brighter than whole galaxies. Its surface is over 50,000 degrees, a blue hypergiant. The fusion inside it is running at a pace that can't last. Stars like this, some models said they couldn't exist. The idea was a star couldn't form with more than about 150 solar masses. The radiation from a star that big forming should push the gas cloud away. But R136A1 is here. It's twice that limit, so astronomers have to rethink how these giants are born. Maybe they come from several large stars colliding in a dense cluster, or maybe the nurseries themselves are more extreme. This star is a paradox. It pushes against the known laws. And it pays for that power. It burns its fuel so fast its life will be short, maybe 2-3 million years. Its end won't be quiet. The theory now is a star this massive might have a pair instability supernova. An explosion so total it leaves nothing behind, no black hole, just a wave of material scattering what it made inside. R136 A1 shows that bigness isn't about how far the surface goes. It's about the weight at the core, the fire inside. From that young powerhouse in a distant nebula, we look back to an ancient light in our own neighborhood. That deep red in the sky, that garnet color, it's from a star, Cephei. William Herschel saw it and called it a fine, deep garnet, and that name, it stuck. It's in Cepheus, a red supergiant swollen. Its radius is something like 1,400 times our Sun's. If you put it where our Sun is, its surface would go out almost to Saturn. That huge, cool atmosphere, that's what gives it that ruby glow. The color tells you about temperature, about chemistry. It means the star has moved past its main life. Inside Cephei, the easy hydrogen fusion, that's long over. The core has contracted, heated under its own weight. Now it's making heavier things, carbon. Oxygen, silicon, building the periodic table right in its heart. And that process, it's turbulent, uneven. It makes the star pulse, its brightness changes. A slow, irregular rhythm, so that steady-looking garnet light we see, it's actually from a massive, unstable furnace, a gem in the sky but with a fiery, struggling heart. It's a star showing what comes after. That beautiful red is the color of a late stage, an advanced one, short-lived, spectacular, and looking at it, you have to wonder about limits. If a star can be 1,400 solar radii, what's the absolute maximum? How big can a star get before physics says no? The Scorpion's heart isn't the only one. The Garnet star either. There's a pair in Cepheus, a duet, but on a scale that's hard to really grasp. The system is called WOH Cephei. Its main star, WOH Cephei A, is a red supergiant. Its size is staggering. The radius is somewhere between 1,000 and 1,600 times our Sun's. That puts it among the largest stars we know. But this giant isn't alone. It has a partner, a smaller star, hotter, blue. They're locked in a slow dance gravitationally, an orbit that takes about 20 years. And from where we are, that dance has a special feature. They eclipse each other. One passes in front of the other. That alignment is a gift, because when the smaller, hotter star goes behind the red giant, its light shines through the giant's atmosphere. That vast, thin atmosphere, astronomers can study that filtered light. They can analyze it. It shows the chemical makeup of the outer layers. It allows for precise measurements. Size, distance. We know the scale of WOH Cephei from geometry, from a cosmic alignment that lets us measure one star against another. But the relationship isn't peaceful. The red supergiant is so huge, its gravity can't hold its outer layers. A stellar wind streams away from it, and some of that material, that gas, gets captured by the smaller companion. The blue star is feeding. It's pulling matter from its larger neighbor. This mass transfer changes both stars. It can spin up the companion, make it rotate faster. It alters their chemistry, and for the giant, it's a slow bleeding, a loss that speeds up its evolution. WOH Cephei is a laboratory. It shows the lives of the largest stars aren't solitary. They can be shaped by partnership, by theft, by a gravitational tug of war that writes the final chapters for both. This binary drama reminds us that in the cosmos, relationships are forces. They can determine how large a star grows, how it burns, how it ends. Cygni is a star in the constellation Cygnus. Its light takes more than 5,000 years to get here. And on that journey, it passes through dust, cosmic dust, which dims the light, reddens it. It obscures what's behind it. This star is a hypergiant, a star of staggering potential size. But its exact dimensions are wrapped in that veil. Some analyses try to account for the dust. They suggest a radius. It could be over 1,400 times the Sun's. If that's right, it's among the largest stars we know by volume. Yet other studies use different models. They propose a smaller figure. This isn't just a measurement error. It's the frontier playing out in the data from a single point of light. The star's luminosity is undeniable. It shines with the power of several 100,000 suns. But the precise details of its size and distance are debated. Cygni is a symbol. It represents stars at the very limit of what our telescopes can clearly see. Our map of the cosmic giants isn't finished. It's a living sketch. Each new observation can redraw the boundaries of what we think is possible. The uncertainty forces a question. If we can't be sure about a star's size from 5,000 light-years away, how do we measure these leviathans at all? What are the tools we use to weigh and measure the universe? The uncertainty points to something deeper. To understand these giants, you need to start with the ruler. Our ruler is the Sun. Its radius is about 696,000 kilometers. That's the baseline, the solar radius. So when we say a star is 1,000 times larger, we're not talking about brightness. We're not talking about mass. We mean its physical size from its core to its surface is 1,000 times that distance. Now, picture the math for a second. A star with a radius 1,000 times the Sun's has a circumference. The distance around its middle, that number is over 4.3 billion kilometers. Light, the fastest thing there is, would take about 4 hours to travel that one loop. 4 hours just to go around the star once, and the volume inside that sphere, that's where the numbers stop making sense. If you hollowed out a star that size, you could fit over 1 billion of our suns inside. 1 billion, our entire star, the anchor of our solar system, becomes just a speck, a single piece in a vast, empty chamber. This scale, it isn't just a big number. It reshapes the star's own physics. Think about the gravity at the surface of something that large. It's actually weaker than the Sun's gravity because the mass is spread so thin across that immense volume. The star becomes a wispy, tenuous thing. Its outer layers are more like a hot fog than a solid surface, and the pressure inside, to hold up that colossal structure against its own weight, the core has to be a cauldron of unimaginable force. Fusion rages at a frantic, desperate pace. This is why the largest stars live such brief lives. They're a balancing act on a cosmic scale, where the outward push of radiation barely wins against the inward pull of gravity. Holding this unit of measurement in your mind, it changes everything. It turns a list of facts into a feeling. The solar radius is our humble meter stick, held up against the impossible. And with that sense of scale in place, the next star on the list doesn't just seem large, it feels monumental. The southern sky has its own giants. Down in the tail of the Scorpion, there's Scorpii. A red supergiant. It's a glowing ember, and its radius is about 1,400 times the Sun's. That makes it one of the largest stars we know by volume. If you put it where our Sun is, its outer atmosphere would reach almost to Saturn's orbit. But Scorpii isn't steady. It's a semi-regular variable. Its brightness rises and falls over hundreds of days in a slow rhythm. That pulsation is the key. The star's outer layers are like a vast atmosphere that breathes. They expand, cool, and dim. Then they contract, heat up, and brighten. That rhythmic breath is a sign of deep change inside. Scorpii has used up the hydrogen fuel in its core. It's left the main sequence, that long, stable phase. Now it's burning helium, fusing it into carbon and oxygen. This new engine runs hotter and faster, but it's less efficient, and the star has swelled into this colossal, unstable form because of it. That instability is what makes Scorpii useful. Astronomers study the link between how long its pulsation cycle takes and how bright the star really is. That period luminosity relationship is a fundamental ruler. By timing the pulse of a variable star like this, you can calculate its true brightness. Compare that to how dim it looks from here, and you can measure its distance. Scorpii and stars like it become mile markers. They help map the scale of our galaxy and beyond. So this southern giant is more than a spectacle, it's a tool. A throbbing heart in the darkness we use to find our place. Its final fate is sealed, but for now, its steady pulse guides us. And as we map these giants across both hemispheres, a pattern emerges. They aren't random, they trace the architecture of the galaxy itself. The record for volume might go to a star in a distant cluster. In Scutum, there's a dense group called Stephenson 2. And inside that cluster, there's one point of light, Stephenson 2-18, a red supergiant. The latest measurements, the ones that try to account for everything, put its radius at about 2,150 times the Sun. 2,150. If that's right, it's the largest star we've ever measured by physical size. To get a sense of that scale, put this star at the center of our solar system. The Sun's surface would be a tiny dot at the very center. Earth's orbit would be deep inside the star. Mars would be inside it. The whole asteroid belt would be inside it. The star's outer layers would stretch out past Jupiter's orbit. They'd brush against Saturn. That's the volume. A single star that could hold nearly 10 billion of our suns. Light from its core would take weeks to reach its own surface. This isn't just a big star. It's a different kind of object. A structure so vast it pushes against the theoretical limits of what a star can be. How does gravity hold something that tenuous together? How does fusion in the core support that immense, wispy envelope? Stephenson 2-18 sits in that strange borderland, where our models of stellar physics start to strain, and its location is a clue. It's in a rich, dense open cluster, a stellar nursery that formed many massive stars. That environment might be key. Maybe interactions with close neighbors early on helped it gather more material. Or the intense radiation pressure in such a crowded place influences how these giants swell late in life. This star is a perfect example of the living nature of astronomy. What we call the largest star today might be revised tomorrow. A new observation, a better model for its distance, a fresh look at the data, and the record could change. Stephenson 2-18 holds the title for now, but its very existence is a question, a challenge written in light, asking how the universe builds its most magnificent, fragile giants. Those stars are bleeding out into space. That deep red glow of a supergiant, it's not just a color. It's a sign of a huge, turbulent atmosphere, and it's streaming away. Slowly, but it's happening. That's the power of stellar winds. For a star like Betelgeuse, the wind isn't gentle. It's a supersonic torrent, charged particles and gas ejected from the star's roiling surface. The scale of the loss is hard to grasp. Every year, a hypergiant can cast off a mass equal to our entire planet, an Earth's worth of matter hurled into the void. Year after year, over 1 million years, that adds up to the mass of our Sun, just given away. This isn't a minor detail. It's the central drama of a giant's final act. That relentless shedding does two things. First, it builds a monument. The expelled gas and dust, lit by the star's radiation, forms a glowing nebula around it. A cosmic shroud. The star is building its own funeral veil from its own substance. And second, it changes the star's destiny. The material streaming away is the star's outer envelope. Its fuel reserve. By casting it off, the star is reducing its own mass, lightening its load. That process determines the final weight of the stellar core. The core that will one day collapse, and that final weight is everything. It decides the ultimate fate. A core below a certain threshold might become a dense neutron star. A heavier core collapses into a black hole, so the stellar wind, this beautiful streaming loss, is the unseen hand. It writes the final chapter. It is the sculptor. The heavy elements forged in the star's heart, carbon, oxygen, iron, they're carried away by these winds. They seed the surrounding space. They become the building blocks for rocky planets, for organic molecules, for future life. The wind from a dying giant is a delivery system for creation. It ensures the star's legacy isn't just a flash of light. It's the raw material for new worlds. So when we see those delicate, glowing nebulae around ancient stars, we're not just looking at a pretty picture. We're seeing a Titan's final gift to the cosmos. And the process that seals its own fate. Once that wind has blown the outer self away, what's left at the center to face the final moment? That final collapse starts with something hidden. A giant NML Cygni. It's one of the most luminous stars we know of in our galaxy, and also one of the largest. Its radius is something like 1,600 times the Sun's. But you can't see it, not directly. It's buried. It sits at the center of this huge, opaque shroud, a circumstellar envelope made by the star itself. For a long time, that dust cloud was so thick it completely blocked the star's visible light. We only knew something was there because of the infrared. The heat leaking out through the dust. This is a star that's vanished behind a curtain of its own expelled material. But that curtain isn't empty. It's one of the richest chemical factories in the galaxy. Inside that swirling cloud, molecules are forming, complex ones. Astronomers have found water vapor, silicon monoxide, and these molecules aren't just sitting there. They're amplifying light. They're creating natural lasers in space, masers, microwave lasers beaming out from all that chaos. So NML Cygni is a paradox. A star of unimaginable brilliance hidden from sight, but its hiding place is screaming its presence across the spectrum. It's a beacon in the radio and the infrared, telling this story of furious mass loss and frantic chemistry. This hidden giant makes you wonder, if a star this significant can be so completely veiled, how many others are we missing? Our list of the galaxy's largest stars might just be a list of the ones we can see. The ones whose light escapes. NML Cygni suggests there could be an entire hidden population. Titans wrapped in their own funeral shrouds, their true scale waiting to be revealed by the subtle warmth they leave behind. That hidden giant points to a universal law. There's a ceiling, a hard line written into the physics of light and gravity. Why aren't there stars 1,000,000 times the size of the Sun? Why does the list stop at a few thousand solar radii? The answer is a balancing act so perfect it becomes a barrier. It's called the Eddington limit. You can think of a star as a constant battle. In one corner, gravity. It pulls everything inward, trying to crush the star into a tiny point. And in the other corner, radiation pressure. The intense light and energy from fusion in the core. That light pushes outward, trying to blow the star apart. For most of a star's life, these two forces are in a stable stalemate. But for the most massive, most luminous stars, the balance tips. The Eddington limit is the point where the outward push of radiation equals the full inward pull of gravity on the star's outer layers. At that precise point, the material at the surface is no longer held down. It's lifted. It's blown away into space by the sheer force of the star's own brilliance. A star that tries to grow beyond this limit by gathering more mass or burning too fiercely doesn't become a bigger, stable star. It starts to tear itself apart. It sheds its outer atmosphere in furious stellar winds. This is why the Hypergiants on our list, like WOH Canis Majoris or NML Cygni, are shrouded in vast clouds. They are brushing against this limit. Their immense luminosity is pushing their own substance away, and this also explains their instability. They aren't serene spheres. They pulse, they swell and contract, their brightness fluctuates. That variability is the star's outer layers breathing in and out, caught in a tug of war they cannot win. The Eddington limit isn't just a theory in a textbook. It's the invisible fence that corrals the largest stars in the universe. It defines the maximum possible size for a stable star. And it tells us that every one of these colossal giants is living on borrowed time, dancing at the very edge of what physics allows. Their incredible light is both their glory and their doom. A force that sustains them and will ultimately strip them bare. The rhythm of a star can be its final song. In Sagittarius, there's WOH Sagittarii. It beats with a slow, colossal pulse. Its radius doesn't stay still. It swells from about 1,000 times the Sun's size out to 1,500. Then it contracts back again. Over a cycle that lasts years, this isn't a small variation. This is the entire star, a sphere of plasma larger than Jupiter's orbit, breathing in and out. One of the largest stars in our galaxy is fundamentally unstable, changing its very dimensions before our eyes. That pulsation is a direct window into the star's struggling heart. For a star this evolved, the internal mechanics have shifted. The easy fusion is over. Now, deeper in the core, heavier elements are being forged. That process releases tremendous energy, but it's erratic. The transport of that energy outward becomes inefficient. Layers of ionized gas inside the star become more opaque. They trap heat. That trapped heat increases pressure, and the star's outer layers are pushed outward in a great, slow expansion. As it expands, those outer layers cool and thin. They become more transparent again. That allows the pent-up energy to finally escape. With that release, the outward pressure drops. And gravity, always waiting, pulls the star's immense atmosphere back inward. The cycle begins again. This link between internal opacity and energy transport is the engine of the pulse. WOH Sagittarii is a textbook example, a key laboratory for astrophysicists. By measuring the precise timing of its light changes and its physical swelling, they can test theories about the final stages of stellar life. The rhythmic expansion and contraction are the death throes of a celestial titan. They are the unstable heartbeat of stellar old age, a sign that the delicate balance of forces is beginning to fail. Each pulse may be casting more of the star's substance into space, a prelude to the final, silent collapse of its core. This grand, rhythmic fade into the long night shows that even an ending can have a terrible, beautiful cadence. All these giants, they fit a pattern. Betelgeuse, Stephenson 218, all of them. There's a chart that shows where they belong. It's the Hertzsprung-Russell diagram. Like a periodic table, but for stars, you plot a star's brightness against its color, its temperature. On that map, our sun is just average, a yellow dot in this band, the main sequence. That's where stars live, fusing hydrogen. It's the middle, but then you look to the upper right corner. That's where the giants are, red supergiants, hypergiants. Not many stars there, but every star on our list is there. Their position tells you something. High up means they're incredibly bright. Far to the right means they're cool, red. To be that bright but that cool, there's only one way. The star has to be enormous. The surface is cool, but there's just so much of it. The total light is staggering. Getting to that corner has a cause. It happens when a star runs out of hydrogen in its core. A star much bigger than our sun. The core shrinks, heats up. It ignites a shell of hydrogen around it. That new energy pushes the outer layers out. The star swells. It becomes a red giant or a red supergiant if it was massive enough. On the diagram, you see this as a path. A star leaves the main sequence. It moves up and to the right. It becomes a titan, so being thousands of times bigger than the sun. That's not a common state. It's a specific phase, a late life phase for the most massive stars. It's a brief chapter, a spectacular one. The diagram explains the fate of every star we've talked about. It tells us why Canis Majoris, Cephei, Scorpii, they're all in the same club. They've reached a similar point. even though they're light years apart. This one graph ties it together. Their huge size, their red color, their instability, what's coming for them. It turns a list of wonders into a story. A story of stellar life and death. With that map, the number of giants starts to make sense. They aren't random freaks, they're milestones on a path that's already been charted. The double cluster in Perseus, it's two clusters really, a pair of them, and in that crowd there's one star you notice, S Persei, a red supergiant. Its radius is something like 1,300 times the sun's. A Leviathan, and it's right there, living in this city of stars. That's not a coincidence, it's location. It's a clue. S Persei was born from the same cloud, the same gas and dust as all the other stars in that cluster. Thousands of them, all siblings formed together. Some of those siblings are massive blue stars. They're still on the main sequence, burning hot and fast. But S Persei has already raced ahead. It's consumed its core hydrogen. It's swollen into a giant. It shines with that cool, red light now. It's the elder statesman. Advanced years, while so many of its siblings are still in their brilliant youth. So studying S Persei here, in this context, it changes the questions. You don't just ask how a single star gets that large. You ask how a star's birth environment, the company it keeps, shapes its whole life. Was it born with more mass because it formed in a richer part of the cloud? Did gravitational tugs from the other nearby stars in that dense cluster influence its spin? Its path and the presence of other massive stars means the cluster is flooded with intense radiation, ultraviolet light, fierce stellar winds. S Persei has spent its entire life bathed in that. That constant exposure, it could have stripped away its outer layers sooner. It could have influenced the chemistry of its atmosphere as it expanded. S Persei shows you a giant star isn't an isolated monument. It's the most prominent member of a family. Its spectacular size, its impending fate, that's a direct product of its birthplace. Its community, it's a reminder that in the cosmos, context is everything. A star's story begins long before it swells to those titanic proportions. It begins in the crowded, chaotic nursery where it first ignited. And just like one giant can stand out in a cluster, other stars stand out too, for reasons that defy our simplest categories. There are other kinds of giants. Not just red, there's a much rarer kind, a more volatile kind, the yellow hypergiants. They burn with a fierce, pale light, not that deep garnet color. Stars like Rho Cassiopeiae, it looks like a modest yellow point in the northern sky, but that's an illusion. It's actually one of the most luminous stars you can see from Earth with just your eyes. Its radius is several hundred times the sun's. It's enormous, but its surface is far hotter than a red supergiant's, so it sits in this strange, unstable middle ground. Astronomers think yellow hypergiants are stars in rapid transition. They might be former red supergiants, stars that have shed so much of their cool outer envelope that the hotter interior is now exposed. Or they could be massive stars on their way to becoming red supergiants, heating up briefly from changes inside. Either way, they're caught between two states. And that in-between existence is violent. Rho Cassiopeiae is famous for its eruptions. Back in the year 2000, it had a colossal outburst. It ejected a shell of material. A mass roughly 10 times that of our entire planet, all in a single event. The star's visible light dropped dramatically. Its surface temperature plummeted as that ejected material cooled. It was a stellar temper tantrum on a scale we almost never see. This isn't a slow, steady wind. It's explosive mass loss. The star is literally tearing pieces of itself off. Another yellow hypergiant, IRC +10420, is surrounded by a complex, expanding nebula. It's this beautiful, chaotic wreckage from multiple eruptions. These stars are so unstable they pulsate irregularly. Their spectra, the chemical fingerprints in their light, change from year to year. They represent a fleeting, tumultuous phase. A giant star in a state of profound identity crisis. It's no longer a cool red titan, not yet a stable blue star. It's a yellow hypergiant, screaming its way through a brief and catastrophic chapter. So gigantism isn't a single destination. It's a turbulent journey with different temperatures, different colors, different kinds of instability. The wild behavior of a yellow hypergiant is a clear signal. The star's internal furnace is recalibrating. It's a last desperate attempt to find balance. It's the prelude, the final violent adjustments before the core itself runs out of options. That final violent adjustment is the prelude. For nearly every star on that list, the ultimate destiny is a supernova. It's the final catastrophic release. In a matter of seconds, the energy from a collapsing core can outshine an entire galaxy. All that immense bulk, the outer layers of the star, are blasted into space. At a significant fraction of the speed of light, that expanding shockwave glows for weeks or months. That's what we see from Earth, a new, temporary star in the sky. But for the very most massive stars, the ones pushing the limits, the end can be even more extreme. A hypernova, an explosion of such staggering energy, it's associated with the most powerful phenomena we know. Long-duration gamma-ray bursts, beams of focused radiation so intense they could be seen across the universe. In these events, the collapsing core doesn't just form a neutron star. It may form a rapidly spinning black hole with jets of material screaming out from its poles. These jets, piercing through the dying star, are thought to be the source. The source of those devastating gamma-ray bursts. The violence of these explosions is almost beyond comprehension, but within that violence lies creation. The intense heat and pressure in the blast forge elements heavier than iron, gold, platinum, uranium, elements that can only be made in the heart of a supernova or in the merger of its remnants. These newly minted atoms are then scattered. They ride the shockwave out into the interstellar medium. They mix with clouds of gas and dust, and there, in that enriched material, the cycle begins again. Gravity pulls these clouds together, new stars form, planets coalesce around them, and those planets now contain atoms. Atoms forged in a stellar cataclysm that happened billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, they were all made inside stars, and the heavier, rarer elements were likely delivered by a supernova. So the death of a giant star is not an end. It's a necessary dispersal, a creative force. It seeds the galaxy with the literal building blocks for everything that comes next. New solar systems, new worlds, the potential for life. This grand cycle of death and rebirth is written in the light of every supernova remnant we see glowing in the night sky. It is the legacy of the giants, a legacy written in stardust and in us. You can't just measure a star with a ruler. It's a puzzle. You solve it with light and geometry. Those numbers, like 1,000 or 2,000 solar radii, they aren't simple facts. They come from indirect detective work. The main problem is angular size. Even the biggest star in our sky, besides the sun, is just a point of light. Its disk is too far away, too small to see, so astronomers have to be clever. They use optical interferometry. That's not one big telescope, it's several smaller ones spread out. You combine their light waves with precision, and you mimic a single, enormous telescope. That virtual telescope can start to resolve the disk of a nearby giant, like Betelgeuse. It can measure its apparent diameter on the sky, but that's only half of it. To turn that tiny angle into a real size, you need the star's distance. That requires another set of measurements, often parallax, the tiny shift as Earth moves around the sun. Each step in that chain has a small error, and those errors multiply. For a star like Stephenson 2-18, tens of thousands of light-years away, the distance itself is a huge uncertainty. A different distance estimate changes the radius by hundreds of solar radii. That's why you usually see a range. Other methods provide checks. Eclipsing binary systems like VV Cephei are cosmic gifts. One star passes in front of another. The precise timing allows for accurate calculations of size and mass, pure orbital geometry. For pulsating variable stars, there's a known relationship between their pulse period and their intrinsic luminosity. Time the heartbeat, estimate the true brightness, compare that to how dim it looks, and you can derive distance and size. But even these methods have obstacles. Interstellar dust dims and reddens the light. It fools our instruments about the star's true color and brightness. A red supergiant's atmosphere isn't a sharp edge. It's a hazy, extended envelope, hard to define where the star truly ends, and some of these giants aren't perfect spheres. They might be oblate, flattened by rapid rotation, or distorted by magnetic fields or a companion's gravity. So when you hear a star is 1,500 times the size of the Sun, understand. It's a monumental achievement of inference, a best-fit model, built from fragments of data across the electromagnetic spectrum. This uncertainty isn't a failure of science. It's the nature of exploring a universe that doesn't give up its secrets easily. Every confirmed measurement of these distant giants is a quiet victory. A testament to curiosity, patiently untangling the light from a dying ember thousands of years old to understand the architecture of a Leviathan. The idea of planets around these stars seems impossible. A star 1,000 times bigger than the Sun would have this huge sphere of influence, but the reality is much more hostile. Take a star like Betelgeuse. It started as a massive blue star. If it had planets when it was young, that system is gone now. When it ran out of hydrogen and swelled into a red supergiant, its surface expanded outward. It would have swallowed the inner planets, Mercury, Venus, Earth, Mars, all vaporized, their material just added to the star's outer layers. The outer planets might have survived for a while. But the heat and radiation would have stripped their atmospheres away, left just barren, scorched cores. The original solar system is completely erased. That giant phase is a cosmic clean slate, but from that destruction, something else can happen. As the star nears its end, it sheds huge amounts of material. Its stellar wind carries away carbon, oxygen, silicon, iron, the ashes of fusion. This ejected gas and dust forms a big nebula around the dying star, and inside that nebula, with gravity and turbulence, new clumps could form. These wouldn't be rocky planets like Earth. They'd be a new generation of worlds born from the debris of the star's death. They're called second-generation planets. Maybe even third. Their substance was forged in the heart of a giant and cast out into space. The idea of a habitable zone where liquid water could exist becomes meaningless here. The radiation from a hypergiant is so intense it would sterilize any world for light years. The stellar wind is a constant sandblasting of charged particles. An atmosphere would be stripped away instantly. Any chance for life as we know it is gone. It shows this cosmic truth. Stellar scale dictates everything. A stable, medium-sized star like our Sun can foster complex systems over billions of years. But a supergiant is a brief, raging inferno. Its scale creates pure extremity. It's a force of creation and destruction. It's not a home, it's a forge. It prepares the heavy elements, scatters them into space, and in doing that, it sets the stage for quieter, stable stars to build new worlds from the legacy of its death. The light from these stars has been reaching us for thousands of years, long before we knew what they were. They were landmarks. Antares, that deep red star, was the heart of the Scorpion. Betelgeuse, with its changing brightness, was the shoulder of Orion. Aldebaran was the eye of the bull. They weren't just lights, they were characters. Stories told around fires, gods and heroes painted on the sky. Their returns were predictable. They helped build the first calendars. They told farmers when to plant. For navigators on the open ocean, these bright stars were fixed guides, constants. They were seen as omens too. Their red color, like blood or fire, linked them to war or passion or change. That cultural imprint is deep. It shows an ancient drive to find meaning in the cosmos. We looked up and saw patterns, narratives, and the biggest, brightest stars were always at the center. Today, that relationship has changed, but it hasn't ended. We don't see Betelgeuse as a shoulder now. We see it as a supergiant, a ticking clock, but the awe is the same. The curiosity is the same. Now we use them as signposts. Their immense brightness lets us see them across great distances. Their pulsations, like with WOH Scorpii, act as standard candles. They help us map the galaxy. So the journey from seeing Antares as a mythic heart to knowing it's a swollen star near supernovae, that's not a loss of wonder. It's an expansion. We've traded one story for a deeper one. The star hasn't changed. Our perception has grown to encompass its true scale. This bridge between the ancient sky watcher and the modern astronomer, it's built on the same light. The same red glow that meant Scorpion's heart now tells us about stellar evolution, about mass loss and chemistry. These giant stars are dual monuments. Monuments to human curiosity across time, and monuments to the universe's own capacity for building titans. Their light is a thread, connecting the campfire to the telescope. The myth to the data. It reminds us that our quest to understand the heavens is one continuous story, where every new answer reveals a deeper question. The giants in our own galaxy aren't the end of the story. To really test the rules of how stars work, you have to look outside the Milky Way. You have to look far outside, into other galaxies. And now, with Hubble and the James Webb Space Telescope, that's what astronomers are doing. They're seeing points of light in galaxies millions of light years away. These aren't supernova, they aren't clusters, they're individual stars, colossal ones, candidate supergiants and hypergiants in Andromeda, our closest large neighbor. And in galaxies so far away their light is billions of years old. It's a huge technical challenge. At those distances, a star 1,000 times bigger than our sun is just a pixel. One pixel, it gets lost in the light of its own galaxy. So the way you find it is by looking for signatures, a fingerprint in the light. These distant candidates are identified by their extreme brightness, by their unique spectra, the chemical signatures that show a vast, cool atmosphere or a hot, furious wind. The James Webb Telescope is especially powerful here. With its infrared eyes, it can see through cosmic dust. It can find the heat signature of these titans, even in crowded stellar nurseries in other galaxies. Every confirmed detection is a triumph of inference, but it's a crucial one. Finding a hypergiant in Andromeda or in the Pinwheel Galaxy, that tells us something. It suggests the physical processes that build a star that immense aren't unique to our neighborhood. The same balancing act happens, radiation pressure and gravity. The same frantic fusion, the same mass loss. It appears to operate under the same rules everywhere. So this hunt is a test of universality. Are the largest possible stars in a distant galaxy the same size as the largest stars here? Or do different environments change the limits, different galactic histories, different amounts of heavy elements? Every point of light that fits the profile of a supergiant, millions of light years away, is a data point. It's a whisper across the void, confirming that the laws we've worked out from our local examples are in fact the laws of the universe. This search pushes our instruments to their limits. But it pushes our understanding further. It turns a list of nearby wonders into a universal principle, a principle written in fire, on a scale that spans the entire observable cosmos. The initial mass is the lottery ticket, A star like Betelgeuse or Stephenson 218, it didn't just drift into that size, it was destined for it from the moment it ignited. The story starts in a violent nursery, a dense molecular cloud, cold and dark. Gravity pulls a clump together, it collapses, spins and contracts, heating up. And if that initial clump is massive enough, 15, 20, even 100 times the sun, it sets a timer. The star that forms is a heavyweight from the beginning. It shines with a fierce blue-white light, burning its hydrogen at a frantic rate. For a few million years, it sits on the main sequence, stable, brilliant. That's its youth, but it's brief. A star with 20 solar masses might live only 10 million years. Our sun gets 10 billion. It's a sprint. When the core hydrogen is exhausted, the balance fails. The core, no longer supported by fusion, contracts under its own weight. It heats up dramatically. That new heat ignites a shell of hydrogen around the core. The energy from that shell burning pushes outward, a tremendous force, and that force does the remarkable thing. It inflates the star's outer layers, pushes them out to staggering distances. The star swells from a hot, compact sphere into a cool, diffused titan, a red supergiant or hypergiant, so the gigantism we see is a phase. Not a permanent state, it's a direct consequence of two things. First, the star's initial mass, won in the gravitational lottery of its birth, and second, its advanced age. It's a star entering retirement, but with a spectacular, expansive finale. Every colossal star is both a product and a process, a product of the violent, chaotic conditions that birthed it, and an active process of self-transformation, as its own dying core reshapes its entire being. They aren't born giants, they are made into giants by the relentless physics of their own burning lives. That initial mass starts something, it sets off a chain reaction. These colossal stars, they're incredibly rare, but they become regulators. They shape the whole ecology of a galaxy. Their influence goes far beyond their own light. A galaxy isn't a static thing. It's more like an ecosystem, and in that system, these giants are the keystone. Their ultraviolet radiation from their hot surfaces, from their winds, it's like a cosmic floodlight. It hits the cold clouds of hydrogen gas drifting between stars, and it ionizes them. It strips electrons away. The gas glows this fierce, colorful light. That's how the most spectacular nebulae are born. The Tarantula Nebula, that huge stellar nursery, it's lit by dozens of massive stars. Stars like R136A1. Without them, that nebula would just be a dark cloud. But it's more than light. The stellar winds from these titans, the shock waves from their supernova, they act like cosmic plows. They slam into the surrounding medium, they compress the gas, they create dense knots, ripples inside the clouds, and in those compressed spots, gravity gets a foothold. New clumps collapse, new stars ignite, so the death of one generation of giants can trigger the birth of the next. They build the stellar nurseries, but their deepest legacy is in the elements. Inside their cores, through fusion, they forge heavier atoms. Oxygen, the oxygen in our lungs, in our oceans. Silicon, the backbone of rocks and sand. Magnesium, calcium, iron, the iron in our blood. All of it is cooked in the hearts of massive stars, and when the star dies in a supernova, it doesn't keep this treasure. It scatters it, it catapults these new atoms back into the galaxy. This process, over billions of years across countless stars, is chemical enrichment. It's why the universe today isn't just hydrogen and helium from the Big Bang. It's rich, full of the periodic table, rocky planets, ocean water, the chemistry of life. It all depends on that enrichment. So when you look at a red supergiant like Betelgeuse, you're not just seeing a dying star, you're looking at a factory. Right now, it's producing silicon, oxygen, carbon deep inside its layers. And when its time comes, it will deliver those materials. It will send them out. So the evolution of galaxies, the chemical makeup of future solar systems, the possibility of planets like Earth. It's all driven by these brief, brilliant lives. By their explosive deaths, they are the ultimate recyclers. They take the primal fuel of the cosmos and transform it into the raw materials for everything that comes next. Right now, our measurements are like a map drawn in dim light. The next telescopes are coming. They'll bring the morning. That 28th star, it's not just a point of light. It's the future of how we see. A future built on the James Webb Space Telescope and the huge ground telescopes being made now, like the extremely large telescope. Together, they'll turn those vague numbers into sharp pictures. They'll let us see the last years of these giant stars not as blurs, but as stories happening right in front of us. The trick is seeing what our eyes can't. Stars like NML Cygni are hidden behind their own dust. For years, they've been mysteries inside these glowing shrouds. But the James Webb Telescope changes that. It sees in the infrared the spectrum of heat. Infrared light goes through dust like a whisper through a wall. So for the first time, Webb can look straight into those chaotic outer layers. It can see the star's actual surface, or whatever acts as a surface in that huge, hazy atmosphere. It can study the chemistry and the structure of the inner nebula, the stuff that's just leaving the star. This isn't just a clearer image, it's seeing the process itself. We'll watch how mass loss actually works, how molecules form and how dust condenses in the violent wind from a dying giant. And from the ground in Chile, the extremely large telescope is being built. Its main mirror will be almost 40 meters wide. That sheer size, that light-gathering power, plus advanced systems to cancel out the blur of our atmosphere, will give us a view of incredible sharpness. Its resolution will be so fine it could, in theory, map features on the surfaces of the closest supergiants. Think about that. We could see the granulation, the huge boiling cells of plasma on Betelgeuse's face. We might find bright spots from magnetic activity or watch massive plumes of material rise and get thrown into space. It would be like watching weather on a star. Together, these tools will take on the big unknowns. Distances will be pinned down with much more precision, turning those wide ranges for a star's size into firm numbers. The dynamics of stellar winds will be measured directly, not guessed. We might finally understand what sets off the huge eruptions in yellow hypergiants. And maybe most of all, we'll have a front row seat to the final years of stars we know are about to die. We could get a continuous, high-definition record of a star's behavior right up until it goes supernova. That data would be priceless. It would test every model of how stars die we've ever made. The next 10 years look like a golden age for understanding these colossal stars. We're moving from the time of the sketch into the time of the portrait, from knowing they're giants to understanding, in close detail, how they live and breathe and how they finally die. This isn't just better astronomy, it's a change in how we relate to the cosmos. We're building the tools to watch the universe's biggest performers not from the back of the theater, but from the edge of the stage. We have our own kind of light, which is the capacity to understand, to stand on a small world and measure a star that could hold 1 billion suns. That's a quiet miracle. It forces a perspective shift, a profound one. It can feel like vertigo. Our entire solar system, from the sun out to the distant comets, would be lost inside the atmosphere of a star like Stephenson 218. Our planet is a speck. All of our history, our triumphs and hardships, it all unfolds on that speck. Set against the billion-year life cycle of a giant star, a human lifetime is less than a blink. In terms of raw physical scale, we are insignificant, utterly, but here we are. We looked up. We built tools to capture light that has traveled for millennia. We decoded the messages in that light. We learned to read the pulse of a star, WOH Sagittarii, like a heartbeat, to interpret the chemical signatures in the shroud around NML Cygni. We deduced laws like the Eddington limit that govern titans we will never touch. This journey, these 30 stars, they're proof. The universe operates on a scale beyond human experience. But not beyond human comprehension. That's the paradox. So the cosmic perspective is a balance. It shows our physical smallness, yes, but it also reveals our intellectual grandeur. We are a way for the cosmos to know itself. The iron in our blood, the calcium in our bones, it was forged in a star that died long before our sun was born. We're not just observers of this grand story. We are products of it, made from stardust. So while our world may be infinitesimal next to a hypergiant, our curiosity gives us a kind of stature. We reach across the light years with our questions, and the universe, in its own way, answers. This reflection, it isn't meant to diminish our world. It's meant to frame it, to see our home, our struggles, our art, our discoveries within this vast context. It makes our achievements more precious, not less. The fact that on this tiny, fragile planet, life emerged that could look out and map the hearts of dying giants, that is a story worth telling. It's a narrative of connection. We are linked to those distant furnaces by the atoms of our being and by the drive to understand. With that sense of connection and scale held in mind, we approach the final entries. The stars that bring this journey to a close. WOH Scuti is a red supergiant. It's in the constellation Scutum. For a long time, it was the champion, the largest star we had ever measured. Its radius was about 1,700 times the Sun's. That number really stuck with people. It became this symbol of size, a star so big it could swallow our solar system many times over. If you put it where our Sun is, its surface would go out past Jupiter. It defined that era. It was the benchmark, the ultimate giant, but science moves. Our tools got better. Our methods for measuring distance improved, for accounting for dust. That record got challenged. Newer looks at the data for WOH Scuti itself suggested it might be smaller. And other stars came up. Stephenson 2-18. Estimates put it as potentially larger. The title moved on. That's not a failure. That's how it works. WOH Scuti's story shows how astronomy actually happens. Our map of the cosmos isn't finished. It's a draft, revised with every new telescope, every algorithm, every observation. Records in science aren't eternal. They're milestones. They mark how far we could see with the tools we had at the time. So WOH Scuti is still an icon. Not because it's definitively the largest, but because of what it means. It symbolizes the drive to find the edges, to look out and ask what the most extreme thing is. Its name became shorthand for a giant star. It inspired wonder. It pushed the idea of scale into people's minds. In that way, it did something more important than just being in a catalogue. It became a gateway, a point of curiosity that led people to look deeper into the sky and the science. As the last specific star here, it's a fitting end. It reminds us this list is a snapshot, a portrait of our current understanding. Tomorrow, a new observation from the James Webb Telescope might find a hidden titan. One that rewrites the list all over again. That's the nature of the search. We end not with a final answer, but with a symbol of the search itself, a red giant in the Shield constellation. It reminds us the universe is always grander, always more mysterious than our latest measurement suggests. And with that, this journey through 30 stars finds a pause. But the story of these giants is far from over. That diversity, it's real, but there's a unity underneath it. These stars, all 30 of them, they're following the same script. Each one started as a massive blue star, born with many times the sun's weight. That initial mass was the ticket. It guaranteed this swollen, final stage. They're not random. They're the natural outcome for any star born above a certain size. Take the physics of a star like our sun and apply it to something 20 or 50 or 200 times heavier. You get these titans. It's a scaling of forces. The frantic fusion in the core pushes outward. Their own immense gravity pulls inward. Late in life, that balance shifts. They expand. They become the cool, red giants we see. So from Betelgeuse to the record holder, Stephenson 218, they're all in the same club. The club of high-mass stars in their final, expansive act. That shared identity means a shared purpose. They're not just ornaments, they're engines. Active, furious engines of change. Their defining feature isn't just size. It's the relentless shedding, that stellar wind streaming off their surfaces. It's a constant donation to the galaxy. They're recyclers. Every atom of carbon, oxygen, iron forged inside them gets carried away by those winds, or it will be in the final supernova. This process enriches space. It turns clouds of hydrogen and helium into the raw materials for new stars, new planets, for life. A star like WOH Canis Majoris, shrouded in its own nebula, it's building the next generation from its own substance. Their gigantic size links directly to this role. The larger and more luminous they are, the stronger the stellar winds, the faster they return that enriched material to the cosmos. Their brief lives are a flash of industry, yet they're wrapped in mystery. Our understanding of their true scale shows human ingenuity and its limits. The numbers we give, 1,000 solar radii, 2,000, they're not simple facts. They're best estimates. They come from a complex puzzle of light and distance and dust. A star like Cygni shows how the same point of light can give different answers. That uncertainty isn't a flaw, it's the science, it's the frontier. Where our telescopes strain to see a star's true surface, to separate it from its hazy, extended atmosphere, every new measurement from something like the James Webb Space Telescope is a step toward clarity. But it also reminds us, the universe's largest structures are among its most elusive. They exist at the very edge of what we can see and define, and this leads to their shared destiny. The thread tying Betelgeuse to R136A1, despite different colors and sizes, is their final chapter. They are all pre-supernova objects. This colossal scale is temporary. A swelling before the catastrophic collapse. Whether they end as a conventional supernova or a hypernova powering a gamma-ray burst, their conclusion is violence and light. That explosion is the culmination, the final, forceful dispersal of all the elements they created. It's the period at the end of the sentence, so the life cycle is a loop. It begins in a cloud enriched by prior giants. It lives a brief, brilliant life of creation and dispersal, and it ends by seeding the future. To understand these 30 stars is to understand a fundamental force. One that shapes a galaxy's evolution, its chemistry, its capacity for building worlds. They are the great catalysts, and in their fleeting, magnificent light, we see the blueprint for everything after. From the shoulder of Orion out to the farthest edge of what we can see, that journey covered a place of pure impossibility. 30 stars, each one a universe of fire all its own. They've changed what we even mean by the word giant. They aren't just static points of light. They're dynamic, they're breathing, they live fast, they burn with a ferocity that consumes their own futures. And they die in explosions, explosions that seed the galaxy, that seed it with the promise of new beginnings. They're the ultimate cosmic paradox, fragile and unimaginably powerful at the same time. Their existence pushes at the very laws of physics. It teaches us that the universe's rulebook is written for extremes, extremes we're only starting to understand. Our methods for measuring them, the geometry of eclipses, the subtle pulse of light, they're a testament to human curiosity. They show that science isn't a list of facts. It's a continuous conversation with the cosmos, a conversation where the answers are often ranges. They're estimates where certainty is hard-won and it's always provisional. This search for scale, it does more than fill a catalogue. It frames our own existence. we stand on a pale blue dot, looking out at spheres of plasma that could contain 1 billion of our suns. The contrast is humbling, but it's also a source of connection, a profound connection, the iron in your blood, the oxygen in your lungs. It was forged in the heart of a star that doesn't exist anymore. You are, in the most literal sense, a child of these giants. Their legacy is written in the chemistry of our world, and in the light of every new star being born from their ashes. So the next time you're under a clear night sky, let your gaze linger on the reddest glows. That faint garnet light in Scorpius or the shimmering shoulder of Orion. Remember, you're not looking at a backdrop, you're looking at a living theater. A stage where titans are playing out their final acts, their magnificent acts, each one a story of transformation, written on a scale that forever changes your perspective.